Hello everyone. Today we're going to talk about lists and vectors and matrices in Mathematica. So the way to define a vector in Mathematica is to use curly brackets and then each element of your vector separated by commas. So this is a vector with elements 1, 2, 3. And if you want to display it in usual mathematic notation, you can use the command matrix form. And here's your vector v. Now, if you want to transform this into a row vector, you could use transform. You could use the command transpose. But in this case, it is not going to work. The reason is that this is a one-dimensional list, and the command transpose works with two-dimensional lists. That means with matrices. So before that command can work, we need to discuss matrices. A way to declare v as a column vector, that's an n by 1 matrix, would be to wrap each element in curly brackets like this. And then if I say matrix form of v, that's again a column vector. But Mathematica knows that now this is an n by 1 matrix, or in this case it's 3 by 1. And to check that, you can use the command dimensions. And actually, to be clear, let's call this v column v column, and let's ask for the dimensions of that. And indeed, Mathematica tells us that this is a 3 by 1 matrix. Whereas if I ask for the dimensions of the vector v that I defined earlier, Mathematica, well, I need to define it again because I've overwritten it. So the dimensions of v is 3. So that's a one-dimensional list with 3 elements. Whereas v column is a two-dimensional matrix with 3 by 1 elements, or 3 plus 1 dimension. Now, if I apply the command transpose to the vector v, that's a column vector, it is going to become a column vector. And in fact, this is the way you would declare a column vector. You would use curly brackets twice and then each element, and then close the curly brackets. So if I ask Mathematica to print this out in matrix form, I can call this v row, and then I ask Mathematica to print that in matrix form, and I see that indeed this is a row vector. So remember, this is a column vector and this is a row vector. Okay, so how does that fit into the bigger picture? These are vectors are special cases of matrices. So if I wanted to declare a matrix, I would first declare the first row like this. And then the second row like this. and then the third row like this. And if I want this in matrix form, you see that first we declared the first row, then the second row, then the third row. So now you begin to understand why a row vector has to be defined like this, because we simply declared the first row of a matrix and then stopped. So that matrix only had one row and 3 columns, so it was a row vector. On the other hand, if we omitted this part and omitted this part and omitted this part, then this would be a column vector, which is what we defined earlier here. Okay, so let's suppose I want to access elements of those vectors or those matrices. So let's remember the vector v. Let's suppose I want to ask for the first element. I would say v and then square brackets 1, close the square brackets, and that will give me the first element. Now remember, you need to have square brackets twice. If you ask for this v square brackets 1, that's not the right thing to do. These brackets are used for functions, not for elements or matrices or vectors. So be conscious of that. In Python or C, this would be used to access elements of vectors, but in Mathematica you have to use double brackets. If I want the second element, obviously it would be v2. You can ask v3 for the third element. You can also ask for the last element, and that would be -1. That's 1 from the end. Or you can use the second from the end. So if I say -2, second from the end would be 2. Remember what v is. So second element from the end is 2. So minus counts from the end. And remember that in Mathematica, elements start from 1. So if you ask for v0, which is what you would do in C or C++, for example, you will not get the first element. Okay. Now, how do we extract elements from a matrix? So in general, the structure will be A brackets and then row and then column. So for example, here's a matrix A again, and here it is in matrix form again. If I say A1, 1, that will give me the element on the first row, first column. If I say 1, 2, that would be first row, second column, and so on. If I want this 6, it is second row, third column. So I'm gonna say 2, row 2, column 3, and I'm going to get that element in position 2 and 3. Now let's suppose I want to extract a whole column of that vector. Let's suppose I want this second column. The way to extract it would be to say A and then all and then the number of the column. So I want all rows, all the rows, and then the second column. So this is it. This is the second column. And I can use matrix form if I want to see that in mathematical notation. Let's suppose I want to extract one of the rows. Let's suppose I want the third row. then I would say the number of the row, which is 3, and then all. I want all the columns. Okay, so this is third row, all the columns. Again, you can use matrix form to write that, but note that now this was a list and it got converted to a column vector once you said matrix form. So again, be conscious of that. That extracted the last bit of the matrix there in the form of a row, but it became a one-dimensional vector after you extracted it. Okay, now let's suppose I want to extract a piece of that matrix. I can say A, and let's suppose I want to extract rows from 1 to 2. I can use semicolon to do that, and then comma as usual, and then rows 1 to 3. Again, use semicolon to do that, and that will extract that piece of the matrix. And again, I can use matrix form to see what I've extracted explicitly. As you can see, it's rows 1 and 2, and then columns 1 through 3. So that's this piece of the matrix. Now, the list representation of a vector or a matrix or a higher order tensor in Mathematica is very elegant, flexible, and if you use floating point numbers, it can be very efficient. This is because it makes use of certain very efficient libraries to do numerical operations. This representation is used in the Lisp or list processor family of programming languages, and modern languages that are inspired by Lisp include Julia and Wolfram Language. And these languages tend to have very simple syntax and very efficient numerical array performance, as opposed to other languages that are more object-oriented, such as Python, where the syntax is going to include objects and it's going to look a bit messy, not as clean, and it's not as performant. Okay, so now let's talk about some numerical operations with matrices and vectors. So let's again define two vectors. So we already have a vector v. Let's also define another vector u. That's 4, 5, 6. If I want to calculate the product of these two vectors, I could use the star command, but that would be an element-wise multiplication. So that would take each element of the two vectors and multiply them together and give me a new vector formed from the product of each element. So 1 times 4 is the first element, 2 times 5 is the second element, and 3 times 6 is the third element. If I want the inner product of two vectors, or the dot product, then I could use u dot v. And that would actually do the dot product. So that would be the sum of all of these elements. By the way, if you want to calculate the sum of the elements in a vector or in a list, you can use total. So if I use total and sum over all of these, that will give me this result. So let's check that. I can use total u star v, and that's that sums over these elements, and that's the same as what's the dot product. And the same is true for matrices, but before we do that, let's talk about another way to do this. So this dot operator is the same as using the dot command. So you could say u comma v, and that would be the dot product between the two vectors, or the inner product. Okay, let's recall this matrix A. In matrix form, we can use transpose A to transpose this matrix and print it out matrix form. And as you can see, this flips the matrix elements about the main diagonal, which is what you could expect the transpose command to do. So it exchanges rows for columns, basically, and leaving the main diagonal the same. Another useful command is the power. So if I say a squared, that will simply take each element of A and square it. But that's not the same thing as the square of the matrix. If you recall, the square of the matrix is when I dot the matrix A onto itself. That would be A dotted onto A and not A squared. So the matrix A multiplied by itself would be this. Obviously you can do that if you want any power. You can just keep dotting A onto itself. But you cannot do that if A is a very high power, or a fractional power, or a decimal number. So in that case, you could use matrix power A, 2, and that will give you the matrix power. And let's just see that in matrix form. And we see that it coincides with that. Can do the third power if you want, like this, and I can ask for the third power, and it's again the correct result. Now we could ask for the inverse of A. Now again, if I use this A to the -1, this would simply take each element of A and invert it. So it's an element-wise operator. It's not a matrix inverse. Or if I do 1 over A, it's the same thing. It would invert each element of A. If I do 1 comma over A, which is something you would do in MATLAB, for example, this is interpreted here to mean that A here is an integer, but if you write 1 dot, then 1 would be converted to a floating point number, and then all operations will turn to floating point numbers. So if you do that, then all of these fractions that were treated symbolically are now treated as decimal numbers. The same is true if I do 1 point and multiply A, or 1 point star A, then this is just A times 1. Okay, so what if I want the inverse of A, the matrix inverse? Then that would be inverse of A. In this case, it doesn't work. This matrix is singular. You can calculate the determinant of A, and you see that the determinant is 0. So that matrix is not invertible. So let's change it up a bit. let's go up here where we entered the matrix. Let's try a different matrix. Let's calculate the determinant of this matrix. Now this is not 0 anymore. So that matrix is invertible. So if I say inverse of A, Mathematica computes the inverse, and it actually did it symbolically, so you get exact results, which is impressive. If I wanted numerical results, I could do this and then convert it to a number. Or I could say, I could first convert A to a number and then invert it. The danger of that is that it may mean some loss of accuracy if the algorithm that does the inversion is not very precise, or if the matrix is not well conditioned. But the benefit is that it happens much faster. So in this case, you see that there is a little error here, 10 to the minus 17, 10 to the minus 18, and so on. You can use the command chop to eliminate these small numbers, and then these are replaced by zeros. Okay, let's delete that. And to check if this is indeed the matrix inverse, you can simply dot it onto A, and you see that you get a unit matrix. Again, you get some small errors. Again, you can use chop to eliminate them. Or you can simply do it symbolically, so eliminate the n here. So inverse of A dotted onto A gives you the unit matrix. By the way to get this unit matrix in Mathematica is to use identity matrix and then the dimension you want. In this case it will be 3, and that gives you the identity matrix of size 3 by 3. Another useful command is maximum. That will give you the maximum element of a matrix or a list. Minimum will give you the minimum. You can use the command eigenvalues to get the eigenvalues of A. In this case, we run into trouble because it has to solve some radicals to calculate them. So let's convert A to a numerical matrix first, and then ask for the eigenvalues. Okay, so now these are the eigenvalues. And if I want the eigenvectors, you can use the command eigenvectors, and Mathematica will give you a list of eigenvectors. You can also use the command eigensystem, and then A, or the numerical value of A. And I've made a mistake here. I've put in some extra brackets more than necessary. So I believe this should be correct. So the command eigensystem is going to give me a list of eigenvectors and then a list of the associated eigenvalues. So I could say values, comma, vectors equals, and that will set the eigenvalues equal to this list and the eigenvectors equal to this list. And then that command will give you eigenvalues and eigenvectors in one shot so that you wouldn't have to calculate it twice, because Mathematica has to compute both to give you the eigenvectors. So if you calculate this command and then this command, you have to do twice the work. So to get both in one shot, you can use this trick. Okay, so now these are the eigenvalues, the eigenvectors, and these can be used to calculate any matrix function, actually. So for example, let's consider the sign of a matrix A. Again, Mathematica will thread through each element of A and calculate its sign. If I ask Mathematica to calculate the exponential of A, again, it will take each element of A and exponentiate it. But of course, that's not the matrix exponential that you know from mathematics. The way we define a matrix exponential, or any other function for that matter, is through a Taylor expansion. So e to the power A, the exponential of a matrix A, is Taylor expansion about the unit matrix. So this is the unit matrix plus A squared over 2 factorial plus A cubed over 3 factorial, and so on. Then if you want to calculate that, you could do it this way. So actually, let's try it this way. So let's try a Taylor expansion from k equals 0 to some power, let's say power 10, and then the coefficient is 1 over k factorial. And then, as we discussed earlier, to raise the matrix A to some power, we can use the command matrix power of A, comma k. And let's sum this series up to 10. Now we got rational numbers because I started with a matrix whose elements are integers. So Mathematica handled this matrix A symbolically. Of course, that's going to be slow if your matrix A is large, and we want to do numerical computation. So let's convert n to a number before doing this. And now we get a numerical result. Okay, so a Taylor series is approximate because you cannot sum infinite terms. If a matrix A was nilpotent, then that series would stop at some power of k, and then higher powers would be 0, so you could get an exact result. But in general, A will not be nilpotent. So there's better ways to calculate exponentials of matrices. In particular, if the matrix A is diagonal, is diagonalizable, then we could bring it to diagonal form by calculating the matrix S, which contains the eigenvectors of the matrix A, and do a similarity transformation. and then if you do that, then you can bring A to the diagonal form, and then it's easy to calculate the exponential of a diagonal matrix because it's simply the exponential of each element in the diagonal with 0 everywhere else. So in Mathematica does all this for you, and you can use the command matrix exponential. There's actually also another way to do it that we'll discuss later, but matrix exponential will give you the exponential of the matrix. Now again, it did it symbolically, so it needs to solve the root of a cubic polynomial here to give you an exact result, but let's convert the matrix to a numerical matrix, so Mathematica can do everything numerically and quickly. And you see that this is a matrix exponential that we get here. It looks like it's not very close to the value we got earlier. So let's try and keep more terms in the series. Okay, so if we keep 20 terms, we get something that's closer to the matrix exponential command of Mathematica. Let's try 30 terms. And now we're getting even closer. Still, we have about 4-5 digits of accuracy. Let's try 50. And now we have more than 6 digits of accuracy. So now both results look the same. Okay, so let's actually, since we know how to calculate the eigenvalues and the eigenvectors, we can try and form this similarity transformation and check if this result is correct. So we have the eigenvectors here. So our similarity transformation is actually formed of these eigenvectors that we calculated earlier, but we have to transpose this matrix. Okay, and then we want the inverse here, and we want this matrix D. Now, to get this matrix D, we have the eigenvalues. So we could say that we calculated earlier. These are the eigenvalues. And then we want to exponentiate them. So let's exponentiate those. And now we want to form a diagonal matrix that has these values on the main diagonal and zeros everywhere else. Now we could do this explicitly, construct a matrix explicitly and have each element on the main diagonal be each of those and every element off of the diagonal be 0. But there's a command to do that exactly automatically. So the command is diagonal matrix. So that will form a matrix that is diagonal, that has 0 everywhere and non-zero in the main diagonal, and you can specify the elements of the main diagonal here. And for example, if I say A, B, C, that would give me a diagonal matrix. And let's write it in matrix form to make it clear. That would give me a matrix with A, B, and C in the main diagonal. In this case, I don't want A, B, C, I want the eigenvalues, so I'm going to put exponential of the eigenvalues in here. And now that formed this exponential, this e to the d that I need. Okay, so now to calculate this exponential of the matrix A, let's call that e to the d. And you need to remove this matrix from here because you don't want e to the d to be equal to this matrix form. You just want it to be equal to this usual list form. Otherwise, Mathematica will give you an error and will not do the operations properly. Okay, so now I want S dotted onto this matrix ED, dotted onto the inverse of S. And sure enough, the result we got here using this similarity transformation is the same result that Mathematica gave us with a matrix exponential command, and it's the same result that we got by summing a Taylor series. Now, there's another way to calculate the exponential of a matrix, or actually any function of the matrix, that's really powerful, and that's using Sylvester's formula and a generalization. So Sylvester's formula can be applied to diagonal matrices, and there's a more general formula that can be applied to non-diagonalizable matrices. And I would encourage you to go to Wikipedia and look up Sylvester's formula, and that's the formula right here. So if you have a function of a matrix A, then that can be expanded using the eigenvalues of the matrix, and that's all you have to calculate. In this case, you don't need the eigenvectors. And then you can calculate the Frobenius covariants of A, which are basically Lagrange basis polynomials. We're going to talk about Lagrange interpolation later and explain what this is, and we're going to come back to this. And that's only if the matrix A is diagonalizable. If the matrix is not diagonalizable, then you can do a Jordan decomposition and make it as diagonal as possible. And then in that case, you can use Hermite interpolation, and then you can use this formula. And again, I'm not going to do it today, but we're going to come back to this after we talk about Lagrange and Hermite interpolation. Okay, so let's talk about a few more matrix operations and list operations. So let's recall we have talked the vector v, and if I use the command total, that will give me the sum of all elements of v. Let's suppose I want the product of all elements. Mathematica doesn't have a command to do that by default, unfortunately, although MATLAB has a command that does that. However, it's not very hard to write your own command. So in particular, in this case, what you can do is first calculate the log of all elements, log v. That would apply the log onto each of those elements, and then you can sum all those elements by saying total. And after you sum all those elements, then you can exponentiate to remove the log. And if you remember your log and exponential identities, this will go through each element of those, and it will form a product of 1 times 2 times 3. So if I do that, that will give me the product of 1 times 2 times 3, which is 6. So you can define your own function, which you can call my list product of some vector or some say vector v, and you can set it with a delayed equal, and then you can use what we wrote earlier, and then I can take this function and apply it to anything. So let's apply to a symbolic list: A, B, C, D. Actually, I cannot use D because it's already B defined. So I can do clear D, or I can use D equals dot, and that will clear the symbol D, and I can use it again for something else. So let's try this function of this list, and sure enough it gives me A, B, C, D, because Mathematica applies the log and the total and the exponential symbolically, and gives me this this product. You could have numbers in here, and it would give me this function would give me the product of these numbers. If one of these numbers is numerical, then everything will become a decimal or a floating point number. So you get a floating point number in the end. Okay, so just to summarize what we've learned today, let's define a vector y as 1, 2, and let's define another vector that's 3, 5. I forgot the equal here. And let's ask for 1 over y. What's that going to do? It will calculate 1 over each element of y. So it will give us 1 over 1, which is 1, and 1 over 2, which is 1 over 2. Now, if you put a dot here, the meaning of that is totally different from what you get in MATLAB. So in this case, dot will simply convert 1 to a decimal numbers or floating point number, and then all operations will be done numerically. So everything you would get here would be a floating point number. So if I do that, instead of 1/2, we get a 0.5, and instead of 1 integer, we get 1.0. I can calculate the sum of x and y, and that will simply add the elements 1 plus 3 as the first element, and then 2 plus 5 as the second element. And I can do x star y. Again, that's element-wise multiplication, so it will do 1 times 3, and then 2 times 5, which is 10. If I want the dot product between those two vectors, or the inner product, I could use x dot y, or I can use dot x comma y, or I can use inner, and then the operation I want is a times, and then let's see if that works. Yes, it did. Now you might want the outer product. You can only do that in 3D, or the cross product. You can look up that using the command, for example, information, and look at outer product, and Mathematica will tell you how to calculate the outer product of the cross vector cross product of two vectors, A and B. Now another command we want to try is x. Let's suppose we want to dot x onto the transpose of y. As I mentioned earlier, this will give us an error. So because y is a one-dimensional list, Mathematica cannot transpose that. Instead, you need to convert that to a matrix that's 1 by n or n by 1. You can do that by enclosing y in curly brackets, and then this command will work. You have to be careful because now I dotted a vector onto a matrix and got a matrix with one element, which is a one-dimensional list. If you want to make sure that it's still a matrix, then you have to enclose that x also into curly brackets. So now you get a 1-by-1 matrix. So remember, each of those curly brackets is one dimension. So vectors are one-dimensional, but matrices are two-dimensional. So you need two curly brackets to show up here. Now, if you have a vector or a transpose of a column vector dotted onto a vector, let's see what happens. So transpose of x. Now, what is the transpose of x? Let's write it out in matrix form. That's a column vector, okay? So if I want to dot that onto y, and let's write that out in matrix form, that's a row vector. So if I dot this column vector onto a row vector, that's 2-by-1 and that's 1-by-2. The result will be a 2-by-2 matrix. So indeed, if I do transpose x dotted onto y, I get a 2-by-2 matrix. And again, I can write that in matrix form like this. And let me close with a performance tip. For optimal numerical performance, one should avoid mixing integer with floating point numbers in the matrices we're using, because this will make Mathematica treat matrices symbolically and operations will be slow. Instead, one should ensure that all matrix elements are of the same numerical type. For example, they should all be 64-bit or FP64 floating point numbers. That will allow Mathematica to use the Intel math kernel libraries and the Intel BLAS subroutines to do matrix operations such as multiplications and so on. And that will dramatically speed up numerical performance and will allow operations to automatically parallelize across all your CPU cores. And moreover, to get even more performance out of Mathematica, you can use a command packed array, and we will talk about that later. Let me type information and then packed to packed. I'm not sure if this will work. Actually, you may have to write developer. To packed array. There you go. And then you can also look that up in the documentation or click here, and that will open up some examples that show you how to use two-packed array to speed up operations, and we'll talk about that later. But for now, I'm just going to say that this array representation has significantly lighter memory footprint. It is cache aware and leads to dramatic improvement in numerical performance. So you're using less memory and less CPU time for numerical operations. And that's taking advantage of some magic that's embedded into the Intel Math kernel libraries, essentially. And more information can be found in the Wolfram linear algebra tutorial that I will link below.